Alright, we are at 1.6 chemical formulae, British, and chemical equations. So this deals with balancing equations, writing chemical formulas, and working with Net-Ionic equations as well. Alright, so the first formula that we are going to review is the ionic compound. So an ionic compound has a metal and a non-metal. To make a crystal or a salt, they call it. And to figure out the formula, you have to use the periodic table to find its charge. These also are can be polyatomic ions or compounds, which just means they contain, polyatomic means more than one different atom. To figure out the formula, you do the drop and swap method with the charges. This causes the charges to be balanced. So if you do the drop and swap right, then your charges are balanced. Alright, so the first thing is to review the periodic table and their charges. Never leave home without it. So the first thing we're going to work with is the alkali metals and hydrogen. So lithium through francium all have a +1 charge. Hydrogen can act as a covalent compound as well, but it's very explosive and generally has a +1 charge, so it is in the alkali family. The second column is the alkali earth. That's beryllium, magnesium, calcium, strontium, barium, and radium. Has a +2 charge. Now how they get their charges is the loss of electrons. So if you lose negativity, you become a positive person. Same thing with these metals, you lose an electron, become positive. So the alkali metals lose 1, and the alkali earth metals lose 2 electrons. Alright, the transition metals all have various oxidation values. There's a handful that only have 1, and we'll get to that. But you have to use the periodic table to determine what charge they have, and you have to use Roman numerals. Alright, the boron is +3, and sometimes they can be various as well, indium and gallium. Carbon family is plus or minus. I put plus or minus because there's nonmetals and metals mixed in, but lead and tin do have various oxidation numbers, so you do have to worry about that a little bit. Nitrogen's -3. The oxygen group is -2. Now you're becoming negative, so that means they had to gain electrons. Nitrogen gains 3, so it's -3, and oxygen gains 2. The halogen family, that's fluorine through acetine, all gain 1 electron, and they gain electrons to be full in their outer shell. And noble gases are already full, that's why they're unreactive, and they have a charge of 0 because they don't need any electrons. Alright, here's some polyatomic ions that you'll be familiar with. You'll get a list in class. Ammonium is basically the only positive polyatomic, NH4+. And then you have carbonate, hydrogen carbonate or bicarbonate, hydroxide, nitrate, phosphate, sulfate. You have your nitrites, sulfites, a bunch of lists we'll get to. Alright, so writing the ionic compound or formula, so you have to use the periodic table to figure out its charge. So you go to magnesium, it's in the second column, so it's a +2. Chlorine is a halogen, so it's a -1. You do the drop and swap, so magnesium's 2 goes to chlorine, that's why it's Cl2. And chlorine's 1 goes to magnesium, you don't write the 1, so it's MgCl2. Sodium nitrate, you should recognize that nitrate is a polyatomic, so you don't have to use the periodic table for that, you just have to write NO3. But sodium's in the first column, so it's +1. Nitrate -1, they cancel out, so you don't have any subscripts. Notice NO3 is NO3. You can't change 3. Then it's not nitrate anymore. Iron 3 bromide, you have the 3 Roman numeral tells you the charge, so you don't have to use the periodic table. bromines and halogens, -1. So you do your drop and swap. The 3 goes to bromine, the 1 goes to Fe, so it's FeBr3. Alright, silver oxide. Now silver is one of those transition metals that do not have more than one charge. It's always a +1 charge. So you notice there's no Roman numeral because silver is always +1. And oxygen's -2. Do your drop and swap, so it's Ag2O. So here they list the 3 major transition metals that don't have an oxidation or various oxidation. Silver, cadmium, and zinc. Silver is +1, cadmium and zinc are +2. So you have to memorize those. Alright, writing the name is a lot easier. All you need to know is their symbol. And then if it's a varying oxidation, you have to use Roman numeral and figure out what the oxidation number is. Zinc we know is always +2, so you don't have to worry about knowing or figuring it out. So it's just zinc chloride. So notice the ending changes from INE to IDE. Here you have lithium carbonate. You should notice that carbonate is a polyatomic, CO3, so it's 2 different elements. So you have to know that CO3 is carbonate, and you have lithium, so it's lithium carbonate. Here we have manganese and oxygen. So you know it's going to be oxide, but manganese is a transition metal, so you have to figure out what oxidation number manganese is. It's either 2 or 4. So you do work a little backwards. So since it's MnO2, that means it had to be double of manganese, so it's a +4 charge. So it's manganese 4 oxide. We can go over the math involved in class if you have a question. Alright, we have calcium and then SO4, again polyatomic, so you just need to know that SO4 is sulfate, so you have calcium sulfate. Alright, some more naming. So here's some polyatomics. So you need to know that SO4 is sulfate, and since it's an ion, it's a sulfate ion. PO4 is phosphate. Here we got sodium, and then you notice sulfate's right above it, so it's sodium sulfate. D, we worked with CO3 already, so it's carbonate. We have calcium, so calcium carbonate, which is very common in mineral in rocks. Basically it's chalk, but it's in rocks. And then we have NaOH, which is sodium, and OH is hydroxide, which is sodium hydroxide, which is commonly known as lye. Alright, more naming continued. We have PO4, you notice the polyatomic, which you gotta know what PO4 is, which is phosphate, so sodium phosphate. Here we have 2 polyatomics, the positive cation and the negative anion. We know sulfate is SO4. We haven't worked with NH4 yet, which is ammonium, so it's ammonium sulfate. Alright, not a polyatomic, AlCl3. So now you know what Al is, which is aluminum, and Cl is chlorine, so it's aluminum chloride. And for IV, we have CaNO3. NO3 is nitrate, Ca is calcium, so calcium nitrate. Alright, covalent compounds. Covalent compounds share electrons, they make a bond, that's how they bond. And it basically follows the periodic table. That carbon needs 4 bonds, nitrogen needs 3, oxygen group needs 2, and the hydrogen halogens can use 1 bond. The periodic table isn't used in naming. It just helps to determine how many bonds. We use prefixes. So you gotta know the basic Greek prefix, mono, di, tri, tetra, penta, hexa, hepta, octa. And that determines the number of atoms. Step 2, or rule 2, mono is never used at the first atom. So For CO2, it's just carbon dioxide. It's not monocarbon dioxide. And 3, no use of the periodic table, so you don't use the drop and swap method. It is what it is. If it's 7 atoms, it's hepta. If it's 2 atoms, it's di. Alright, so let's look at a couple examples. We have carbon tetrachloride. So notice carbon there's no prefix, so it's 1. Tetra means 4, so it's CCl4. Oh, the dangerous dihydrogen monoxide. That is one of the leading greenhouse gases, and it contributes to many deaths around the world. Drowning, which is H2O, dihydrogen monoxide. Sulfur hexafluoride. So anytime you say sulfur hexafluoride, you gotta say sulfur hexafluoride because it raises or lowers your voice. Helium raises its voice. Sulfur hexafluoride drops its voice. Sulfur, there's no prefix, so it's 1. Hexa means 6, so it's SF6. Fluorine dioxide, no prefix for fluorine, so it's 1. Di means 2, FO2. Alright, naming. It is what it is, so you just gotta know how many atoms there are and use the right prefix. Here we have SBr5. 5 means penta. The first element is sulfur, so sulfur pentabromide. NO3, it's not nitrate because there's no ion there, no charge. So nitrogen is single, so it's just nitrogen, and 3 oxygen, so it's trioxide, nitrogen trioxide. H2S, there's 2 ways to write this. We know there's 2 hydrogens, and there's 1 sulfur, so you could say dihydrogen monosulfide. Some people write dihydrogen sulfide. So that mono is not set in stone. Z or XE F8. 8 means octa. XE is xenon, so xenon octafluoride. Alright, moving on to balancing chemical equations. So remember that atoms on each element must be the same value on both sides to be balanced. That's what balancing means. So if you have 5 hydrogens, you need 5 on the other side. Quick review of a balanced equation. You have your reactants on the left-hand side of the arrow, products on the right-hand side. You have the yield sign, and you have coefficients, numbers in front of each compound or molecule or atom. Notice oxygen O2 doesn't have a number, so it's 1, not 0. Alright, so let's do the practice. We have liquid ethanol, notice liquid, burns with oxygen gas, gas, produce water vapor, which is a gas, and carbon dioxide, you should know that it's a gas. So why did I preference liquid gas? Is because they're their states. So we write their states. L for liquid, G for gas. There's also AQ for aqueous, and S for solid. Alright, carbon inventory. Atom inventory. How many carbons are there? There are 2. How many hydrogens? There's 6. And oxygens, there's 3. Remember, in oxygen, there's 2 here, but in ethanol, there's an extra oxygen. Do the same thing on the right-hand side. 1 carbon, 2 hydrogens, and 3 oxygens. So we need to balance. Oxygen's balanced, which is great, but it's not going to stay that way. So we want to leave oxygen till the end because it's in different molecules. So we can do hydrogen or carbon. Carbon's always generally first. So that means we need to put a 2 in front of CO2 to make C turn to 2. That also changes oxygen to 2 times 2 is 4, plus 1 from water, which is 5. Okay, so that does change high oxygen, but it balances carbon. So that means we move on to hydrogen. So we got to put a number in front of H2O to make it 6. So what times 2 gives you 6, and that is 3. 3 times 2 is 6, so it changes hydrogen to 6, which is balanced, which is great. But it also changes oxygen to 3 plus 4, 7. 3 from the water, 4 from the CO2. So here on the left-hand side, the reactant side, you gotta do a little subtraction and addition. Notice there's 1 in ethanol, which is good because we can make it odd because we have 7. We need to get to 7. So that means we can get this oxygen to 6. So what times 2 gives us 6, and that's 3. That changes to 6 plus 1, which gives us 7. Is it balanced? Yes. So we're good to go. We're ready to do any stoic or any analysis on the problem. Alright, homework question. So this is going to be due when you walk into class. It's 3 problems to write and to balance. So you got to know its chemical equations and to balance the chemical reaction. Use states. So you got to remember what state iron is because it doesn't tell you, but it tells you aqueous hydrochloric acid, HCl, if you didn't remember. Then it tells you a solution of iron 2 chloride and hydrogen gas. Aluminum hydroxide decomposes. That means it has to be a solid. So you gotta know aluminum hydroxide is a solid. It decomposes into solid aluminum oxide and liquid water. And then you have liquid hexane, burns in oxygen, oxygen's a gas, form carbon dioxide and water vapor. So that one's pretty similar to the previous example. Alright, net-ionic equation. So a net-ionic equation basically means you have ions that are in water, a solution, they would say, which means aqueous, and it writes the reaction that only involves the ions that do something. The ions that don't do anything are called the spectator ions. Basically like a sporting event. You have a football field, the people are in action playing, the football players are the net-ionic equation, and then you have spectators cheering them on. It's like, hey, go chlorine, hey, go sodium, yay, okay. And then, so the ionic equation is just the ions that are involved, no spectators. So here's an example. You can see what happens when you add zinc to copper sulfate. Notice the copper sulfate blue color gets reduced to a faint blue. Okay, kind of cool reaction. And you have copper forming on the zinc. Okay, so first step is to balance the equation, which is balanced already. 1, 1, 1, 1. Next is to break apart the solutions into their ions. So you can't break apart zinc because it's a solid. So you break apart copper sulfate and you break apart zinc sulfate into their ions. +2 for copper, -2 for sulfate, +2 for zinc, -2 for sulfate. 3. Cross out the spectator ions. That means there's no change in state. So you go to each part. Zinc goes from solid to AQ, not a spectator. Copper goes from AQ to solid, not a spectator. Sulfate goes from AQ to AQ, that is a spectator. They get zapped. That wasn't really a good zap. Anyway, so step 4 is to write now the net ionic. So we write everything but the sulfate. So it's just Zn solid plus Cu2 plus yields Zn2 plus Cu. Check that it's balanced. Notice the charges on the left hand equals +2. Charge on the right is +2. So we're good. Here's another example. Magnesium hydrochloric acid makes hydrogen gas. Great stuff. And an aqueous solution of magnesium chloride. So you look at each part. Mg goes from solid to AQ, not a spectator. H goes from AQ to gas, not a spectator. Chlorine goes from AQ to AQ, so chlorine is the spectator. So the final equation would be Mg plus 2H plus yields Mg2 plus hydrogen gas. Notice it's balanced, 2 hydrogens, 2 hydrogens. That means there's a total 2 plus on the left hand, a total 2 plus on the right, so you're good to go. Alright, here we have an acid-base reaction. Sulfuric acid plus Li, sodium hydroxide, yields water and sodium sulfate. Check your parts. H goes from AQ to liquid. Sulfate goes from AQ to AQ. So sulfate would be a spectator. Na goes from AQ to AQ, spectator. OH goes from AQ to liquid. So the Na and the SO4 cancel out because they're spectators. You bring down 2H plus 2OH and it makes 2 waters. Simplify it because you have all common numbers. So it would be H plus OH minus yields H2O. Alright, a precipitation reaction. Basically you have a precipitate you form. Okay. And then you have to write the net ionic from the precipitate reaction. So you're gonna, sorry, I'm trying to pull a video for you. Because every time I think of PPT, I always think of Naughty by Nature. And
I'm Bo Jackson. I'm an all-star.
Wrong one. Here you go. Naughty by Nature. Word. So every time I think of PPT, I think of OPP. So, you know, a little music, give you guys relax a little bit. Alright, back to PPT reactions. So all you care about is the solid. So, in an example, you would have a precipitation reaction. Double replacement reactions are typical PPT reactions. So you really focus on the solid. So the solid here, zinc hydroxide. So you only care about zinc and hydroxide. So that means Na and Cl will be spectator ions, which is true because Cl is AQ and Na is AQ. So you only bring down what you need, in this case only zinc and hydroxide, and make sure you bring down the coefficients. So you would have 2 OHs and 1 zinc, and you would make zinc hydroxide. So that's the net ionic for precipitation reactions. So you only care about the solid. Here we have a iron sulfate plus NaOH, and you make FeOH2, which is the solid, and Na2SO4 is AQ. So here you only care about is FeO2. So you bring down FeO2, bring down your Fe. We know it's plus 2 because sulfate is 2 minus. So Fe has to be 2 plus. And you bring down OH. We know OH is minus 1. Make sure it's balanced. And you have your net ionic for a PPT reaction. Alright, one of my favorites, you make lead iodine because it makes a really cool yellow precipitate. So you only care about what you're making, which in this case PBI2, solid. So you bring down lead and iodine. That means K and NO3 are spectator ions. So your reaction would look like lead 2 plus. We know it's 2 because the 2 from here, from nitrate, because the drop and swap. 2I minus 1. We know iodine's